Hi everyone, it's your instructor here with a short video lecture about continental drift and geomagnetism. I want to start today's lecture by discussing a famous German meteorologist named Alfred Wegener. Wegener is well known because he was the first to hypothesize that the continents used to all fit together to form a single supercontinent, which he named Pangaea, a name that lives on today. And in the picture here, this clustering of continental landmasses was considered Pangaea. Of course, our globe doesn't look like that today. Wegener proposed a hypothesis called continental drift, which posited that the continents are mobile, and therefore they would have once been together to form Pangaea in the past, like what's shown here, but over time those continents move and drift relative to one another, thereby producing the arrangement of continents we see today. Wegener had a lot of good evidence for this, but he didn't have a mechanism to explain how the continents moved. In the next few slides, I'm going to very quickly walk you through what those lines of evidence were. Clue number one of Wegener's, the fit of the continents. And perhaps you've noticed this yourselves, that the eastern part of South America kind of does this bend out to the east, whereas the southwestern part of Africa has a similar concavity. Well, that was noticed long ago by many people who suggested that maybe South America and Africa once fit together. Same is true with this kind of convex curve of Africa and the concave curvature of eastern North America. Another clue was the location of past glaciations. We will discuss later in the semester how geologists can determine what parts of the earth were once glaciated, but it is possible to do. And once people started studying the glacial records on the continents, they saw that at the same time in Earth history, it appeared as though southern Africa, southern South America, southern India, and most of Antarctica were glaciated. Oh, in southern Australia. Curious because these places are, of course, near the equator today, or many of them are. This suggested that not only were these locations, like southern Australia and India, close to one of the poles of our planet, but that they were probably once together in the same place. So this was a key line of evidence that argued for the continents having moved such that they were joined together and close to one of the poles. Here's another kind of cartoonish rendering of a map showing India, southern Australia, Antarctica, southern Africa, southeastern South America, all joined together and all near one of the paleo-Earth poles. Clue number three was the distribution of climate belts. This is very similar to the distribution of glaciations. So just as glacial records appeared to be similar across many continents that are now near the equator, what was also observed were similar belts of swamp-related rocks or arid desert-like rocks, things that were recording different types of climate and depositional systems. And when you put all of those together from across the various continents, they seem to line up to create these belts like you're seeing here. So this would have been like the tropical belt. And then you had the kind of desert arid belt. And then of course you had the belt down here with the glaciers. So this also suggested that the continents were probably once together, making something like Wegener's Pangaea. Clue number four, the distribution of fossils. So this is a photograph of the Glossopteris fossil. This is a very famous fossil because it's found in South America, Africa, India, Australia, and Antarctica. Of course, these are places, I mean, think about India and Antarctica. They could not be more different in terms of their locations and positions relative to the poles and the equator. The climate of India is nothing like the climate of Antarctica. So how is it possible that a plant could have existed in both continents? That is only possible if those continents were together and in a different climate setting sometime in the geologic past. Same could be said for creatures. There are fossils of some creatures that could not migrate across entire oceans, and these fossils are found in different continents today. So take, for example, the fossil Mesosaurus. It lived in both Africa and South America. Either that exact same species of animal had to evolve separately but create identical species in both continents, or Africa and South America were once together. Mesosaurus lived and roamed across both of these when they were joined together as Pangea, and they have since split and moved relative to one another such that Africa and South America are now separated by a large ocean. Lastly, matching geology. So just as we saw climate belts and glacial belts that extended across various continents, so too do matching geologic features such as mountain belts. So in this picture, we've got big swaths of really ancient, stable continental crust. That's what's shown here in the green things. And then we've also got these mountain belts, which are shown in kind of the brown stippled or kind of cross-hatched areas. And what you can see is that they appear to go right across the continents. So again, suggesting that the continents were once together, but that they have drifted relative to one another to their present-day positions. Just another map showing kind of the lining up of some of these global mountain belts. For example, it's believed that the mountains that make up, these are very old mountains that make up the western part of Europe, are the same mountain belts that you can find in the eastern part of Greenland, suggesting that these two were once joined but have since moved apart relative to one another. Okay, so it turns out that Alfred Wegener did have many lines of very convincing circumstantial evidence. I mean, when I walk you through all of those clues, you're probably saying to yourself, like, yeah, duh, it's obvious. The continents must have been together at one point and they have since separated. But actually, when Wegener took his ideas to scientific meetings and had discussions with other scientists, he was laughed out of the room and considered he was generally disregarded as being silly and having crazy ideas. And unfortunately, his ideas would not be believed, and he would not be vindicated until after he had died tragically on an expedition to the Arctic. So let's talk about how we have since come to understand that Wegener was, at least in part, correct. To do that, we need to talk about the Earth's magnetism. The Earth, as I've told you before, has a bar magnet that extends through its core. That magnetic field that is set up because of that bar magnet is generated by the liquid outer core. And the liquid iron moves and can generate this magnetic field. The axis of Earth's magnetic field is not the same as the rotational axis of planet Earth. So the magnetic pole is shown in the blue dashed line, and the geographic pole is shown in the yellow-orange straight line. And you can see that they are almost 12 degrees offset from one another. But regardless, the Earth's magnetic field, which is again set up by the liquid outer core, creates, you can think about them as like lines of magnetic particles that move around the exterior of the Earth, that block solar radiation, and that also protect us humans from all sorts of cosmic radiation. And it provides important clues to the evolution of our planet. We know that the North Magnetic Pole has been roughly near the North Pole going back at least 1,800 years, but it's wobbled. It's moved around a little bit. So this red line shows the trace of Earth's magnetic North Pole as it's kind of like wobbled and moved around just a tiny bit, but remaining in these high latitudes near the geographic North Pole. The magnetic pole and the geographic North Pole are not parallel. I've already showed you that they are about 11.5 degrees apart from one another. But that difference varies depending on where you are on planet Earth. We call the difference between the two poles, so one axis and the other axis, whatever that angle is, it can vary. We call that angle the declination. Okay, and again, it differs depending on where you are on the planet. When you use a compass, it is measuring magnetic north, and if you want to learn about where you are with respect to geographic north, you have to set the declination on your compass to account for that difference between the magnetic axis and the geographic axis. You can think again about Earth's magnetic field setting up this kind of like a force field of magnetic particles. Maybe you could think about them as being little iron filings that are tiny and moving about in the exterior of our planet. And these magnetic filings are going to tilt according to the magnetism that exists in the Earth. So these magnetic particles are going to tilt very steeply. In fact, they're going to be at nearly a 90-degree angle at the poles, but they're going to be very flat or have a horizontal or 0-degree angle at the equator, at the magnetic equator. So these lines of magnetic force, they tilt or they dip according to the way that the magnetic field gets generated and flows out from one of the poles, wraps around the Earth, and comes back in to the other pole. That tilt is called inclination. So inclination refers to the tilt of Earth's magnetic field at any given latitude. So inclination is very different at the magnetic equator than it is at the magnetic pole. And you can have all angles of inclination possible between 0 and 90. What's very cool about our Earth is that when some rocks cool and crystallize, they lock in the magnetism that exists in planet Earth at the time that that rock cooled. That means that a rock that came from, say, a hot lava might have iron-rich minerals in it that are moving all around and energetic. They're mobile when the rock is molten, when it's lava. But when it cools down, those iron-bearing minerals lock in the Earth's magnetic field at that time and at that place on our planet. That is what is known as the paleomagnetism of the rock. So all, or many rocks anyway, if they contain iron-rich minerals, contain some record of the paleomagnetism of the Earth at the space and time that that rock cooled. It's very cool. Anyway, we can sample a rock and determine both the magnetic inclination and declination of that rock when it cooled. So again, hot lava, no magnetization because the iron-rich minerals are moving around in the rock. They're mobile and they're energetic and they are in motion. But once the lava cools and solidifies to become a basalt, those iron-rich filings, which are iron-rich minerals in that rock, then become locked in parallel to Earth's magnetic field. So Earth's magnetic field in this picture is doing something like this, and you can see that the minerals in the rock itself are parallel and are locking in that Earth dipole at the time. Here is a picture of the rock type basalt. Okay, so basalt is very good at locking in magnetism because it contains abundant iron-rich minerals. On the left here, we've got a hypothetical stack of basalts that may have crystallized over time, say in a cliff face in Hawaii. So 600 years ago, you erupt a lava and it cools and it makes this basalt layer, we'll call it A. 500 years ago, you erupt some basaltic lava and it cools and it makes layer B. 400 years ago, you create basalt layer C, etc. What we have observed is that if you look at a stack of basalts, again, say in a cliff face in Hawaii, these different layers record different magnetic inclinations and declinations. That's what's shown here in these little diagrams. These are the inclinations that are being recorded. These are the declinations that are being recorded in each of these layers. The fact that these layers are recording variable magnetism means either one of two things. Either one, Earth's magnetic field has to be moving all around the planet. So Hawaii's not moving, it's staying in the same place. The lavas are being continuously erupted over time, but Earth's magnetic field is apparently wandering such that the lavas record different declinations and inclinations. That's one possibility. The other possibility, of course, is that Earth's magnetic pole is not moving or only moving very, very minor amounts, but is staying mostly near geographic north and south, but that the continent of Hawaii is moving relative to the poles. So this diagram is intended to show the two different scenarios that could possibly explain the hypothetical data shown on the previous slide. If the continent is fixed, then the magnetic pole must move. Conversely, if the magnetic pole is fixed, then the continent must have moved. We figured out which of these is correct by looking at lavas erupted in other parts of the planet. So we have our data from Hawaii, but let's go get data from similarly aged basalts in Europe or in Australia or some other place. If the magnetic pole is moving, if it's the magnetic pole that's moving, then those places should record the same changes in magnetism. If the pole is staying fixed in one place, then those basalt stacks in Europe, Australia, other places should record different apparent polar wander paths. And as you can see here, the African apparent polar wander path, the European apparent polar wander path, and the North American are all very different. This tells us that the continents have to be moving relative to Earth's magnetic pole. And this is what vindicates Alfred Wegener and shows that at least to some extent, this concept of continental drift is true. I'm going to sign off here with a quiz question. So take a moment, read this question, pause your video. We will discuss it when we meet back up together on Thursday. See you then.